Hi everyone, I am going to talk to you today about chapter 9.3, and we're going to do hypothesis tests about a difference in proportions. So like I've said to you lots of times, this is kind of like more of the same. All of this is going to be really similar. It's really nothing new. Well, I should say it's very little new. We're just kind of putting things together in like a new way. So we're, running a hypothesis test for, like we said, the difference in two proportions. So the whole idea behind this is that we want to say, is there a difference in these two proportions? So is there a difference? Well, if there weren't a difference, so if P1 and P2, proportion 1 and proportion 2 were essentially equal, if there weren't a difference, then the difference in those two would be equal to 0. So that's kind of our null hypothesis. Remember, our null hypothesis is always like the status quo, kind of like, like the norm. So that's what we're assuming is true. That's our H0. That the two proportions, and when I say proportions, I'm specifically meaning the population proportions. Notice we're just using P1 and P2. The two proportions are equal. So let's look at this quick example. Researchers designed a study to compare the proportion of children who come to school without eating breakfast in two low-income elementary schools. An SRS of 80 students from school 1 found that 19 missed breakfast today. At school 2, another SRS of 150 students had 26 who missed breakfast today. So more than 1,500 students attend each school. Do these data give convincing evidence of a difference in the population proportions at the alpha equals 0.05 significance level? So notice the questions about the population, right? We, just like before, we have data, that came from a sample, and we can, see if there's a difference in the sample data. But we want to know, does that give us evidence? Does that sample data give us evidence about the population? So right now we're just going to state the appropriate hypotheses. So we're going to assume that there's no difference, right? There's no difference between the population, and let me click one more time, the population percent, or the true proportion of all students at school 1, minus the population percent of, or true proportion of all students at school 2 who miss breakfast. We want to assume that there's no difference between those two things. That's our HO, or our null hypothesis. Our alternative hypothesis, HA, is that there is a difference, because they don't really specify. If I go back on this question, to this question real fast, they don't really specify like, oh, I think school 1 has more students who miss breakfast or whatever, right? Notice they're saying, do we have convincing evidence that there's a difference, okay? So again, when we state our hypotheses, we don't look at the actual sample data. We look at the question that's being asked. All right? And we defined our parameters of interest right here. So there's our hypotheses. So keeping in mind with any hypothesis test, we're assuming that the null hypothesis is true. That's the whole point of a hypothesis test. We assume that the null hypothesis is true, and then we look at our evidence that we've gathered from, like, our sample data to see if the evidence gives us, to see if the sample data gives us evidence that maybe HO isn't true. So we call the common values of these two parameters P. Or in other words, what happens if these things are equal? So in order to figure out, well, if they were really equal, it's kind of like P1 and P2, if they were really equal, it's kind of like they came from almost like the same place, right? So we're kind of combining, we're going to combine P1 and P2 as if they came from one larger sample. So we call this our P combined. C for combined. So C stands for combine. So you're going to notice we have P hat C. You essentially just take all of the successes from both sample, add them together, and then how many total people did you survey in both samples, and you divide them together. So that's your p hat combined. So let's talk about conditions, all right? So in our conditions, these again should look really familiar. We've seen these now like a lot of times. But the data have to be random. So that could mean that they come from two independent SRSs, kind of like the example we just looked at. We can assume because that our sample data came from two different schools that they were independent and they told us that it was a random sample, okay? So the other option, remember we talked about if you're doing an experiment, we don't always have the opportunity to take a random sample for various reasons. So if we didn't take a random sample, that's okay, as long as when we designed our experiment, we broke our subjects up randomly. So the two groups came from a randomized experiment. So that's our random condition. Now, if the two groups came from a randomized experiment, we don't have to check the 10% condition. But if they did come from two independent random samples, again, kind of like the one that we just looked at with the cereal, or with the missing breakfast, sorry, we do have to check the 10% condition and make sure that the sample size is less than 10% of the population size for both school 1 and school 2, or whatever the case may be. Now, here's kind of like the tricky part. So again, remember, we're running a hypothesis test or a significance test. We are assuming that HO is true, right? So if we assume that HO is true, that there's no difference between, P1 and P2, we took that combined P hat. So the large counts condition, we're no longer looking at like N1 times P hat 1. We're looking at N1 times P hat combined. So notice all of these are P hat combined, P hat combined. So it's how many successes and failures do you have in each group, but compared to what we're assuming to be true, which we're assuming that we can combine the P hats. So that's a little tricky. All right, let's look at an example. So researchers designed a study to compare the proportion of children who come to school without eating breakfast. Same example we just looked at, right? We want to just check the conditions, check if the conditions for performing the test are met. So we kind of already talked through some of these, but they are independent because they came from the two different schools. They did specify that both of them were SRSs, and because they were independent SRSs, we do have to check the 10% condition. So they also at some point told us that about the population size, that there were about, or I should say, more than 1,500 students at each school. So there were 80 people in the first sample, 150 in the second sample, and that's less than 10% of 1,500 in both cases. So the 10% condition, we do have to check it, it is met. In order to figure out, in order to check the large counts condition, and remember, this is so that we can assume that our sampling distribution is approximately normal, so that we can use our Z star or our Z score. We need to find or to calculate the P hat combined, okay? So you're literally just going to combine the two samples. What would happen if I combine the two samples? So we had 19 who missed breakfast at school 1, 26 who missed breakfast at school 2, so 19 plus 26. We had 80 total students sampled, 150 total sampled, 80 plus 150. So our P hat combined is 19.6%. Then we take that 19.6% and we multiply sample size from school 1, so 80 times that 19.6% is 15.68. And then 80, so again, sample size 1 times 1 minus 19.6%, so 80.4%, is 64. We need all these numbers, remember, to be bigger than 10, greater than or equal to 10. And then we do the same thing with the sample size from school 2. So 150 times that combined p hat, and 150 times 1 minus that combined p hat. All of these are bigger than 10, greater than or equal to 10. So large counts conditions tells us that the sampling distribution should be approximately normal. So our z-score is essentially meaningful. All right, so as we know now, our standardized test statistic is always equal to the statistic minus the parameter divided by the standard deviation of the statistic, right? Now, remember, on your formula sheet, you're going to have to kind of like build this formula, right? So this is what you're given on the formula sheet. Let's figure out what each piece, you know, where each piece kind of comes from. The statistic, so the statistic is like the data we collect, but we're looking at the difference between the two p hats, right? The parameter, remember, our null hypothesis was that the two p's are equal. So the difference we're testing to see, is it 0 or is it something different? So the parameter here is 0. The standard deviation of the statistic, right? So we know that when we combine the sampling distributions, like of these two proportions, this is the formula that we would use, right? And this is going back a couple chapters now. So here's the thing. Remember that when we do a hypothesis test, we're assuming that the null hypothesis is true, right? So if we assume the null hypothesis is true, this whole sampling distribution that we're assuming is true is based upon your combined p hat, not, in other words, we don't want to replace the p hats, I'm sorry, the P1 and the P1, the P2 and the P2 with p hats. We don't want to do that. Instead, we're going to use this denominator here. So we're going to use the combined, or sometimes that's called pooled. You should be familiar with that terminology as well. We're going to use that combined formula for the standard error. Okay, and again, the reason we do that is because we are assuming that HO is true. And if we assume HO is true, then we're assuming that P1 and P2 are equal, so we should combine those. There's your formula. Now, I just want to come over, I'm going to drag over my formula sheet because you know I'm big on like making sure that you can kind of build this formula. Okay, so here's my formula sheet I have pulled up here. You know, I'm kind of, this is like a small little window here. But standardized test statistic, and we know that this is going to be a z because, remember, we're assuming like normal distribution. Statistic minus parameter over standard error of the statistic. Again, the statistic, the difference in the p hats. Parameter, 0 because there should be no difference, or we're assuming no difference. Standard error of the statistic. Scroll down, right? We're talking about proportions, so I'm looking at this table, proportions. I go all the way over to the right side, standard error. And this is two proportions, so I'm down here. So you can kind of think of this one of two ways. If P1 and P2 are equal, you can think of like factoring out this numerator here. And this formula for standard error is the same thing as this here. So you could just sub this in for the denominator there. Or you can use this formula, but remember, you don't want to use P1 and P2. You want to use, I'm sorry, you don't want to use P hat 1 and P hat 2. You want to use P hat combined for both. So that's how you would kind of build that formula. All right. All right, now we have our formula. Let's look at another example problem. Let's revisit this one. We're going to ask or answer some different questions. So same idea about looking at students who come to school and don't eat breakfast, right? Part A, explain why the sample results give some evidence for the alternative hypothesis. So remember, our null hypothesis was that the two proportions are equal. Well, 19 out of 80 and 26 out of 150, those aren't equal. So that right there, the observed difference, in other words, like the data that I collected in my two samples are not the same. I didn't get the same exact result, right? So the difference in the sample proportions is not equal to 0. So that's some evidence that says, you know what, maybe the population proportions are not equal, or maybe the difference in the population proportions is not equal to 0. But remember the whole idea of sampling variability. Even if the difference in the two proportions was actually 0, so even if the difference in P1 minus P2 was actually 0, if I were to sample over and over and over and over and calculate all of these differences, sometimes when I sample and calculate the difference in my P hats, sometimes these differences and these little dots I'm going to draw, you know, you've seen me draw this a bunch of times. These little dots I'm going to draw are the differences in the P hats, right? Sometimes those differences might be 0, but a lot of times they're going to be a little bit more than 0. And maybe they'll be even kind of like a decent amount more than 0. But sometimes they're going to be a little bit less than 0 as well. And remember, again, sampling variability, this distribution is going to be approximately normal, right? All right, so we do have a little bit of evidence, but that doesn't tell us like for sure. We need to run the hypothesis test to see for sure. So calculate the standardized test statistic. So in order to do that, we need the p-hat combined. We already did that. That was our 19.6%. We did this previously. The standardized test statistic is a z-score. Remember, we just built that formula. So it's the difference in the two p-hats. So p-hat 1 minus p-hat 2 minus 0. Because we're assuming, right, the parameter, we're assuming that the difference is actually 0. And then divided by this whole thing. Notice p-hat combined is what we use down here. We don't use p-hat 1, we don't use p-hat 2. So listen, you know I've said this to you a lot of times about all these other tests, hypothesis tests, and confidence intervals. You're not actually ever going to put this into the calculator. I would definitely type this in wrong and make a mistake, right? I'm going to show you in a minute how to use the calculator to get this. But your z-score, your test statistic would end up being 1.17. So how do I calculate my p-value? Well, remember, this was a two-tailed test. This was our alternate hypothesis was like a not equal to, right? So in order to calculate your p-value, you need the probability that z is greater than or equal to 1.17. Here's my picture. But then we're going to multiply that probability by 2. So 2 times 0.1210. So our p-value is here. And that's using the table. You can also always use the calculator, right? So based upon our p-value, in other words, there's a 24% chance that I would get a difference of, what was the difference again? Let me go back. You know, about like 5% or more if I were to assume that the difference was actually 0. So that p-value is pretty high and very high compared to the alpha. So that means that we're going to fail to reject HO. We don't have convincing evidence that there's a difference in the actual true proportion of the students at the schools who skip breakfast today. And remember, my conclusion is about the population, the actual true proportion. It's not about the sample. I know what happened in the sample. I know what happened in the sample. The samples were different, but we're making a conclusion about the population difference. All right, so hopping over to the calculator, all right, we're going to use the calculator to kind of run this hypothesis test too. So you're going to see this on my screen here, but or on my PowerPoint, but I'm going to bring over my calculator to show you too. So you know all these tests and confidence intervals are under this menu. I can go to Stat and then scroll over to Tests. And then I can just scroll down. It's important to know the name of each test or confidence interval because I just think it makes it a lot easier to use this menu. So remember, this question was about proportions, the percent of people who are students who don't eat breakfast or the proportion. We have two different samples. So this, and we're doing a hypothesis test. So this is like option 6 here, this two proportion Z test. So scroll down, or you can just select the number 6, hit enter. Now here's where you enter in all your data. So from school 1, we had 19 students who didn't eat breakfast out of 80 students that were sampled. In school 2, we had 26 who didn't eat breakfast out of 150 who were sampled. And then you have to be careful because you need to select what is your alternative hypothesis. In this case, it was a not equal to, right? We were saying the two proportions were not equal to each other. And then I scroll down, I hit calculate, and look, this spits out all the good stuff that I need to know. So it does the number crunching for my Z-score. I should not actually ever plug that crazy formula. And this is the crazy formula I'm referring to. Let me click back a couple slides. Right? I should never plug this crazy formula into my calculator by hand. I should always let the calculator do the number crunching, right? So here's the Z-score. Here's the corresponding p-value. Let's make sure that matches up too, right? So look, my p-value that we got either using the table or using like the normal CDF function was 20.24. Look, p-value is here. And then it also gives you the sample proportion, so the p-hat from first sample, p-hat from your second sample, and this p-hat here is your p-hat combined. Remember our p-hat combined that we calculated by hand by adding up, you know, the raw data? We got 19%. Here you go. There's your 19%. All right, so this calculator, when you do this 2-prop Z test, it gives you like, it spits out like everything you need. Where were we? Okay, so again, just another reminder, don't do the number crunching by hand, use the calculator. So in summary, here's your summary for what should your test statistic be for a 2-sample Z test. We've seen this, we kind of build it. Just as another quick reminder, I'm going to say it a million times. We're assuming that HO is true. We're assuming that there's no difference between the two population proportions. That's why we use our p-hat combined as our standard error of the statistic, all right? All right, let's look at one more example. So high levels of cholesterol in the blood are associated with a higher risk of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? The Holinsky, I'm not sure I'm saying that right, sorry. Heart study recruited middle-aged men with high cholesterol but no history of other serious medical problems to investigate this question. Look, no SRS, right? No SRS. But the volunteer subjects were assigned at random. So I'm giving you like a preview of what's to come, but there's our randomization, right? This was a randomized experiment. So 2,051 men took the drug gemfibrozol, to reduce their cholesterol levels, and a control group of 2,030 men took a placebo. So during the next 5 years, 56 men in the treatment group, I'm going to call it, and 84 men in the placebo group had heart attacks. So do the results of this study give convincing evidence at the alpha, equals 0.01 significance level that gemfibrozole is effective in preventing heart attacks. So listen, remember that alpha level is set at the beginning, right? And then we're going to interpret our p-value that we're going to eventually get. But so we're going to run through this whole hypothesis test real fast. So here's our important information. So first thing, we always have to talk about what is our parameter of interest and what are our hypotheses. So remember, when it's a two-sample test, we're always assuming that there's no difference between the two populations. Again, your hypotheses are always about the populations. And so the question is, if I read question A, do the results of the study give evidence that the gemfibrozole is effective in preventing heart attacks? In other words, that the people in this group, would they, or the people that take that medication, would they have less heart attacks than the placebo group, right? So if I were to kind of write this out, in other words, the people in the treatment group should have less heart attacks than the people in the placebo group, right? Well, in order to get my alternative hypothesis to kind of look like that, I can subtract from both sides, right? And so in other words, that's saying the proportion of heart attacks from the G group minus the proportion of heart attacks from the PL group or placebo group is going to be less than or equal to 0. And notice when we define our population parameters, we're specifying that we're talking about the population, the true proportion of heart attack, or the true heart attack rate, or like proportion of people who have heart attacks for all middle-aged men, right? All right, now, what type of test are you going to do? You need to make sure you name your test. This is a two-sample Z-test for the difference in proportions. So let's check our conditions. So the random condition, remember we specified that we didn't take our data, our men from simple random samples. Specifically, they said that they volunteered, but we did take those men who volunteered and we randomly assigned them to the two groups. So that's our random condition. And because we didn't take an SRS, we don't have to check the 10% condition. So we're good with that. So then we have to check the large counts condition. Again, remember, we are assuming that HO is true. We're assuming that there's no difference in the two groups. So if there were no difference in the two groups, it's kind of like all of these, 4,000 plus men all came from the same group. So we find our p hat combined. So 56 who had a heart attack in the treatment group, 84 in the placebo group, and this is the total number of men who were involved in the study, right? So our p hat combined is 0.0343. When we do our large counts condition, we need to use that p hat combined in our multiplication, right? So how many expected successes should we have from the G group, I'll call it, and how many failures from the G group should we expect, and then how many expected successes from the placebo group, how many expected failures from the placebo group. And remember, success isn't always a good thing. In this case, the success means that the person had a heart attack. All of these numbers are greater than 10, so that condition is met. Okay, so let's keep going. We need to find our test statistic, right? Our Z-score. So again, use your formula sheet. I'll slide it over here for 1 second to build your test statistic, and get used to doing that, because guess what, guys? You're not going to have this formula, on the AP exam. You're going to have to build it from the formula sheet. So I would start practicing that now as you're doing these practice problems. But anyway, so our P hat G is 56 out of 2051, or in other words, 0.0273. P hat placebo group is 84 out of 2030. So look, it looks like there's a difference. 2.73% of men from the treatment group versus 4.14% of men from the placebo group. It looks like there's an improvement, but is the improvement statistically significant? That's the question. Or could it have just happened by chance? In other words, because of sampling variability, right? That this is just so happened to be what happened in this one sample. All right, our p-hat combined, we already found. That's there. So plug in for your test statistic, p-hat G minus p-hat placebo. The parameter is 0 because we're assuming there's no difference. In the standard error formula that's down here, all of the p-hats are p-hat combined, right? And then 1 minus p-hat combined, 1 minus p-hat combined, divided by the sample sizes, the individual sample sizes. Again, you're not going to do this by hand. You're going to do this on the calculator. But your test statistic is negative 2.47. So another quick reminder, even though you're doing the number crunching on the calculator, you still have to write down all of this work. So I would essentially be writing down all this work, and it would be, if I were doing this problem, it would be at this point that I get out my calculator, and let me clear this. I go into stat, test, to proportion z-test, and I type in 56 men out of 2,051 and 84 men out of 2,030 had a heart attack, right? And this one was a less than, right? Yeah. So I go over here, I scroll down, I hit calculate. So it would be after I wrote this down on my paper, that's when I would use my calculator to get that negative 2.47, right? That's my test statistic. This also, like we said before, spits out your p-value, and your p-hat 1, you can check to make sure you got that the same, p-hat 2, that, and then plain old p-hat on here, remember that's your p-hat combined. All right, so what else do we write on our paper? Here's the picture that we would draw to get our p-value. And then let's draw our conclusion. So answer the question. Essentially, this is where we're kind of answering the question. Our p-value is really pretty small. It was 0.0068, right? And that's definitely less than our alpha value. Remember, our alpha value we set in the beginning. So we're going to reject HO, and we're going to say that we do have some evidence that the middle-aged men who would take this gemfibrozole drug would have a lower heart attack rate than those who only take a placebo. So we do have evidence to say that this drug was more effective than the placebo. So that's our hypothesis test. So look, as a quick reminder, there's this one little question, right? It's this one little question. Do the results give convincing evidence, right? You have to write everything that we just saw out. All of that has to be written out in order to be able to answer that question. None of it can be left out. You use the calculator to do the number crunching, but everything else has to be written. Now we're going to interpret our p-value. So remember, in order to interpret the p-value, our p-value was 0.0068. You're assuming that there is no difference in the population proportions. So again, this is going back to, remember this like sampling distribution we've been looking at? You know, in our sampling distribution, it would be centered at 0 if we were to calculate all of the possible values for the difference in the two p-hats. So we're assuming that this sampling distribution is true, right? And that there was no difference in the effectiveness of the two treatments. So assuming that there's no difference in the effectiveness of the two treatments, there would be a less than a 1% chance, so a 0.0068 probability of getting a difference in heart attack rates for the two groups of this was our observed difference or less just by chance. So again, just because of the sampling variability. All right, that's it, guys. So in this section, again, it was all about two proportions, the difference in two proportions, and running a hypothesis test based upon that. Do your practice problems. If you have questions, please ask. Thanks for watching.